Okay, well, this presentation, there's an introduction, then we talk about the transmit receive switch prerequisite, a requirement really if you're going to do this sort of experimenting. A little bit on transmitting mag loops as a reference, and then I'll cover receive only active mag loops, and then cover off the experimental designs that I've been playing with. There's about 5 of them. And then some tests and assessment of how they worked. I've got a comment on broadband commercial active loops, and that might invoke a bit of discussion at the end, or questions or even opinions, because I don't have a great deal on that. And I'll also go through some built examples, so I will go blow by blow through the 5 different loops that I'd made, and then come to a summary and conclusion for this presentation. So the magnetic loop antennas seem to be increasing in popularity, particularly recently, and this is borne out by the sheer volume of stuff that's available on the net. If you type in active mag loop or just mag loops generally, you'll get an awful lot of stuff. And a key attribute that seems to have been rediscovered by many is the small physical size of these antennas that can be used in the 3.5 to 30 meg HF bands. This makes them an attractive solution, particularly in urban environments where space for antennas tends to be quite limited. But another important attribute is the improved signal-to-noise performance that you get on receive compared to larger conventional wire antennas. The bandwidth of these antennas, though, is very narrow and could be regarded as a trade-off, or the trade-off, to achieve its small size. So this means the antenna is tuned to a single frequency, and if it is to be used at different frequencies, you would need some form of variable tuning. To be effective as a transmitting antenna, care is also needed to ensure that the main loop and capacitor connections are of low resistance, in the order of a few milliohms, and the lower transmit efficiency of a mag loop antenna compared to an ideal full-size wire antenna. I'll bump that, sorry, accidentally. The lower transmit efficiency of mag loop antennas compared to an ideal full-size wire dipole is often pointed out by the armchair theorists without appreciating that very few people have an ideal antenna in the first place. And I think this is when people realise this, that they find that these things actually work pretty well. It's difficult to derive an objective and measurable comparison with any real practical meaning because of the different radiation pattern and different takeoff angles you would get between these arrays, a loop array, and say an ideal dipole or an ideal vertical, or whatever it is you're drawing your comparisons. The online loop calculators that you can use and that are widely available often put in there a reference to an ideal loop as a reference for the various dimensions considered in each design. And that's actually quite useful because you can use that to evaluate your design, and there's sort of measures that are reasonably attainable. Using an active mag loop receive only antenna as another variation of mag loops, which is what we're talking about today. And they provide the benefits of a low noise receiving system without having to meet the stringent low ohmic loss array that's required for transmitting. That means they're a lot cheaper to make and are easier to experiment with. A prerequisite, though, if you are wanting to transmit as well, is the transmitting radio amateur will have to have a TR switch to allow the separation of the receive antenna from the usual transmit antenna. Some people do have radio transceivers that already have a receive-only port, so you wouldn't need one of these switches, but they're not actually that common. Most people don't have that. So let's just look at what the TR switch is if you're going to use one and want to transmit as well as receive. The TR switch is a standalone unit that allows any amateur station to be configured to automatically operate with separate antennas between the receive and transmit modes. And on here we can see there's a receive antenna. We'll talk about the receiver protector later. I'll actually explain what that is. That's the station TR switch. And then over here, you've got the transmit antenna. And if you want to use a linear, you can bung that in there. And then here's your transceiver down here. This feeds into this port. So your receive antenna is fed into that port and your transmit antenna into that port. So thereby having separated, you've separated the receive transmitter from, the receive antenna from the transmitting antenna. Just looking at that switch for the moment, and we won't go into detail. Whoops. I've got one of these silly mice. It's a Apple mouse. If you brush your finger over it, it does things that you don't expect it to. Never mind. I'll try not to use the mouse. I'll use the keyboard. So this is a TR switch, a homemade one, and the details of this are covered actually in another paper on our website. In today's noisy and urban industrial environments, a wire antenna array may transmit efficiently, but is not necessarily the optimum array for low noise reception. And in densely populated areas, the large and extensive wire antennas will pick up a lot of electronically generated noise, and many switch mode power supplies and etc. that are used in your house and the neighbour's house. So therefore, a separate antenna array using active loops possibly and electronic phased arrangements for reception can provide improvements in receiving performance. So this is why people use these switches, so they can play around with their receive antennas and get lower noise reception. So a separate receive antenna somehow needs to be integrated into the station's transceiver in a convenient way. And this is what this TR switch does. So as you can see, there's a simple point here where you connect your transceiver in the center there. You plug your whatever receive antenna you want to use and you transmit antenna in here. And this port here is the PTT line, which goes press to talk line, which goes back to your transmitter. And in here there's a delay that simply delays a relay that switches backwards and forwards between this receive and transmit mode. And we won't go into the detail of that here, but that is covered on our website. Looking briefly at a mag loop designed for transmitting will provide us with some context before we go and look at the receive receive only active loops. If we look at this here, we can see that the key component that determines a mag loop's efficiency is frequency dependent. And for a variety of reasons, the practical optimum loop conductor length is 1/5 of a wavelength. And then the value of a tuning capacitor across that sets the resonant frequency of that loop. Now, using the online calculator, an example that I use and is fairly reliable is the OH7SV. That's all you have to type into Google and you'll get it. Can be used to find the optimum loop size and the capacitor value for any frequency of interest from presumably from 160 metres to 10 metres. Note that we talk about loop length, but in practice the loop diameter will be that length over pi, which is about 3.14. A reasonable transmit efficiency will result of 10 to 13 mil coaxes used for the loop conductor. That means RG213 or even Heliax LDF 450, or even fatter coax if you've got it. Now, to illustrate, the 4 bands 80 metres, 40, 30 and 10 are presented here, and their dimensions look like this. So the way this table works, and it's a simplified version of a detailed table that's in a separate paper, which we'll talk about in a moment. We've got the band here, 80, 40, 20, 10. This is the frequency that the loop design is based on for each of those bands. This is the loop length, so in other words, the total length of the loop conductor, and that's divided by pi to get the diameter of the loop. So that's going to be your practical physical size of the loop. The capacitor that you need. Okay. I guess you saw that, John. Our meeting has been extended indefinitely, so we don't have to log in again later.
Good.
You got that? Good. Okay. So again, explaining this table, for this size loop, the capacitor you need is to tune it to that 3.7 megahertz is 53 picks. And the output is -2 dB below an ideal loop. At 40 metres, same sort of drama. There's say it's 7.1. If it's an 88 metre long loop, it will give you a diameter of 2.6, and you'll need 39 picofarads to tune that. And it gives you an output of -1.9 dB or 1.9 dB below the ideal loop. And again, down here, 1 dB and 1 dB below there. So basically that represents some dimensions that are built for loops that are almost at the optimum size, being 1/5 wavelength, in each of those bands. So that's what they would normally look like, and that's the range of values we're talking about for the capacitor. For some reason, we've done that. Right, that's transmitting loops. Now, for receiving loop design parameters. Unlike a transmitting loop, the loop conductor losses are not critical for good performance on receive. For example, 16 gauge wire, that's 1 millimetre steel wire, was used in my experiments and tested to good effect. The loop size is also less important for receive. And for example, the 80 metre band loop length of say 1/10 to even 1/20 of a wavelength resonated with a much larger capacitor has been tested and works remarkably well. Coupling the tuned loop to the receiver is the role of the active part of the antenna, which will make up for some of those losses that I've just described. Matching to the 50 ohm receiver feeder is achieved with a balanced high input impedance amplifier based on the FET BJT preamps used for active whip antennas. We'll see the detail of that in a moment. This high impedance only very lightly loads the tuned circuit of the loop and the capacitor, and takes advantage of the voltage magnification that normally occurs in a tuned circuit. The significant advantage of the tuned loop is the exclusion of strong unwanted RF signals other than the frequency the loop's tuned to, and this overcomes a major failing of broadband active loop or active whip, for that matter, that can suffer from severe intermodulation effects from out-of-band signals, such as broadcast stations or the ham down the road. The best experimental loop that was built to test these ideas in this paper was Design 3, made from 3 meters of LDF 450 semi-rigid coax, and we'll look at the other designs in detail later under built examples. The tuning and active part is included in the next slide. And somehow that's not quite right, because it's the one after that. Sorry. So that's the experimental active loop, which is just under 1 meter in diameter. And so we'll come back to that, the details of what's in that in a moment. This here is a picture of the active loop amplifier. This circuit is simply, this part here is, some will be familiar to some of you as the amplifier that's used in the active whip antenna. And if you just look at that, you can see, well, we've built to put another one down here and simply slapped a transformer to take the output of the 2 of them to feed into 50 ohms. And then over this side here, we've got that's the loop, which is shown as an inductor, a fixed capacitor, and then a variable capacitor to fine tune that loop. So this is simply the active part of the experimental loop. And this was the amplifier that was used for all of these experiments. There's a biflar wound transformer at the end here, which takes the output of this half and the output of this half. And there's a clever little thing here that actually allows you to feed 12 volts onto the feed line, and it gets separated out down here by by this bit of clever wiring here, which doesn't actually require an RF choke, because it's just the configuration of this. You might want to ponder that later. But this is the MFJ approach to their active antennas. They use this also for their active whip antennas, this clever little arrangement here where there's a virtual earth put on, well, there's an earth put on here, RF earth put on here, but there's actually volts there, which is this, the 12 volts is here, connects through here, through the transformer. So kind of using the transformer to isolate the DC from the RF. I thought it was clever anyway. The experimental loops were quite extensively and repeatedly tested on a range of signals near and far from the Churton Park QTH, in other words, my place, over several weeks. So it hasn't been a flash in the pan. Regular nets with participants around Wellington and even Otago ensured that a range of signals and conditions to prove these loops on 7055 was used. Their performance, from my point of view, was a huge improvement compared to the signals from a 6-band vertical in the same location. Although vertical antennas are well known for poor electrical performance, but the 6BTV has proved to be really good for transmitting. And while it's a lousy receive antenna here, the combination of a 6BTV vertical and the active mag loop has transformed the usefulness of this place as a home station. The optimum direction of the 6BTV with good earth radials ensures effective transmission, while a small active mag loop located above a metal roof of the dwelling gives good receive signals in an otherwise electrical prone urban environment. The degree of noise improvement in general is estimated as around 10 dB. This is a reduction in noise of about 2 S points on a signal meter compared to a conventional wire antenna. Other amateurs who use mag loop antennas will be nodding at this point, and will understand that, yes, that would be right. The interesting thing is that it has, as I said before, it's actually absolutely transformed my ability to participate in nets where you've got very, very low signal levels and high noise here. Now, just a comment on broadband loops. Again, if you go onto the internet and look up mag loops or active loops in particular, and broadband, you don't even have to put in broadband, they're almost invariably broadband because they're easier to make. Many commercial products are offered in that range of 150 to 30 megahertz, and obviously they don't need tuning. There are also numerous DIY projects for shortwave listeners that are broadband loops, and some claim loops give better signal to noise ratio performance compared to a broadband active whip, and this is probably believable. The key words for searching for these and having a quick look around are the MLA 30 loop on eBay, and that's $75 NZD, and the Wellbrook loop ALA 1530, which is $400 NZD. Now, I've not tested any of these broadband loops, and I'm not rocking them, but a major potential failing of them, and comments have been made by quite a number of users, is they can suffer from quite severe intermodulation effects from nearby RF and even out-of-band signals such as strong FM broadcast stations. So quite a few amateurs have commented on that. And here in Churton Park, we have an AM radio station on the other side of the motorway over in Granada, or somewhere over there. There's quite a lot of RF over there. And Mount Kaukau is pushing out a lot of RF in the 100 meg band. And when you stick an aerial up that's got some active componentry in it, all of that stuff and all that crap comes into your antenna. And I've picked up quite a lot of intermodulation effects here from that. But a significant advantage of the active tuned loops described in this paper and presentation exclude strong RF signals because your tuning element is right at the beginning of the receive chain, and it's a high Q tuned circuit, so it just doesn't get in and anywhere near the amplifier. They're very effective for that. So design one was a thin wire. Loop. We're looking at now looking at the construction details of these active mag loops. Design one was a thin wire active loop. It uses a loop length of about 3.5 meters of 16 gauge 1 millimeter galvanized wire, fashioned into a diamond shape and supported with a fiberglass fishing rod and a square brace of 1.2 meters, which I'll show you the picture in a minute. It's quite a small antenna with pretty low wind loading. And it can be resonated with about 150 picofarads. In practice, I used 130 picofarads with a 65 picofarad trimmer across it to get it to work on a 7055. And that's a picture of it there. That's the fishing rod there. There's a piece of fiberglass rod across here, and that's this piece of 1 millimeter wire that turns up here on this little box, which has got the active part of the antenna built into it. And over here we've got the preamp box, and it's a waterproof box with a couple of stainless steel studs sticking out the top of it. And so one end of the loop comes down here through the rod, round and up there, separated from the other one that comes here through the rod and round here to there. So they're not joined. It's the gap in the loop there, and that runs into coax down here, down the pole to the inside. As you can see from this, it's a pretty simple antenna. It's quite flimsy, and its dimension across here is 1.2 meters and 1.2 down there. So it's a little over a meter in diameter. Design number 2, this was a semi-rigid mag loop, and it was fixed tuned. The loop length was 3 meters, and sorry, I just lost my paper here. 15. Matching to the 50 ohm receiver feeder is achieved with the same balanced input amplifier used for all of these versions of active mag loops. And using semi-rigid 13 millimeter Heliax, 3.3 meters long, a more robust and circular shape is fashioned, as you can see here. The main purpose of the thick Heliax is it does make a self-supporting loop, which obviously you're not going to get with 1 millimeter wire. But for a transmitting loop, it would be desirable to use this because of the low loss, but you don't actually need it for the receiver for its low loss property. It is still a convenient building material. This loop is temporarily taped to a carbon fibre pole for testing, so that's what's holding it there. And the tuning capacitors and preamplifier are contained in that waterproof plastic box you can see at the bottom of the loop. And the powered feeder is sealed at its entry to the box with epoxy glue down here. And the loop conductor enters the box via a special gland fittings that are waterproof with silicone sealant. So they come in down here. That's actually sealed with silicone, so that box is absolutely waterproof. Now, design number 3 is the one we looked at before. This was the best of the lot. This is the prototype 7 megahertz tuned loop antenna mentioned earlier. It has a motorized tuning capacitor that allows remote fine tuning to any frequency within the 7 to 7.3 meg band. And the motor requires 12 volts at 30 milliamps and is a 1.5 RPM high torque model. It uses semi-rigid 13 millimeter heliax, and the tuning capacitor values used are 10 to 100 picofarads, which happen to be in parallel with 100 picofarads as well to get it to sit into the right range. And that's a picture of it there. This one's got an extra cross piece on it to make it more rigid. And it's got a much larger box. That's more for the box is more for as an anchoring point for the bottom of the loop to make it stronger. And the contents of the box are shown here. The box is 220 millimeters high, 150 wide and 55 deep. Again, it's one of those electrical boxes with a piece of seal in it that pushes down and makes it waterproof. What we have in the box is quite a large motor, a 1 RPM motor, the one from a Chinese thing, which probably I think cost about 20 bucks. A bit of plastic tube here to isolate the motor from this capacitor. All of this is bolted down onto a piece of plexiglass or acrylic. The variable capacitor is here. It's a brass one with one side of the capacitor connected to the heliax and the other side of the capacitor connected there. And then the balanced input amplifier is just in here and just put into the side of this here to feed into the coax, which comes up around here. And in this picture, it's not sealed there, but normally I'll put a blob of two-pot epoxy in there to seal that, and that would completely seal that box. The epoxy hasn't found its way there yet. To tune that, obviously, if we step back, we see the motor here. There's a couple of wires that whiz out here. These are applied to the motor, and to turn the motor of the capacitor in one direction, you connect it to the volts, and you reverse the volts to reverse the motor. And simply, for the purposes of testing, the box is just a plastic box like that with 2 push buttons on it. And the wiring of it is such that you can't push both buttons together and short out the power supply. It's interlocked, so only one button will apply power in the correct phase or polarity to that motor. There is an improvement that can be done here, and that would be to use switches wired to short out the motor when it's de-energized. This is something which Ted had done with his in his work, it's ZL2TB, because what it does then is if you short the motor out when you take your finger off the button, the motor stops dead, so you don't get the run on that you otherwise get if you use it just use that configuration there. The only trouble is I didn't have enough other contacts on the switch to put a short across the motor when it was in the rest position. Now, design number 4. This design here is just a theoretical design only, based on this calculator, and the details of this are in the published paper, but it gives all of the capacitor values for all of these bands, 30, 40, 80, 40, 30, 20, 16, 14 and 12. Just a point to note is that for a smaller loop would be needed if you actually wanted to go down to 10 metres. You'd have to reduce the loop size to about 640 millimetres. Other antennas may be regarded as more practical above 20 metres anyway. I'm not sure that you would want to use loops all the way up there. And remote tuning could use varactor diodes in place of a motor drive of a variable capacitor. So that's another piece of work that would be worth experimenting with. And finally, design number 5. This is a wire diamond mag loop antenna for 80 metres. And again, it used about 7 metres of 1 millimetre galvanised wire fashioned into a diamond shape. It's less than 1/10 of wavelength and size, so it's a bit under the optimum size. The capacitor range you need for that is, for 3.5 megs is 172 picofarads, and at 3.9 megs, 135. So the range for the band is 43. So the trick there is you would use a variable capacitor of say 50 picofarads in parallel with a fixed one. Then the preset capacitor and a FET preamp is mounted in a waterproof box. And that antenna is shown here. I'm not sure the definition of this at your end, but we've got this trusty Black & Decker that's just holding the vertical support. We have a cross piece across here. That's 2.4 metres from there to there, and 2.4 metres across there. And so this here is the wire loop. The box, picture of the box is over here, and it's just a potting box with a couple of studs out at the top with the amplifier in here. And again, it's a pretty small antenna for 80 metres. It looks pretty flimsy, but it will probably handle the Churton Park winds. So I wouldn't have any problem putting that up on the back fence if I was going to use it there. And it works remarkably well. And this is what happens after you've done a whole lot of experiments. You end up with a whole lot of crap like this against your back of your shed. Again, I'm not sure the definition of your pictures at your end, but certainly in the paper you can see that this one here is the 7 meg loop. That's the big one, which was 2.4 metres from tip to tip. And this is the best antenna, which was the one just under 1 metre diameter, made out of the rigid coax with the big box on it there. And that's my favourite aerial because it works very well. I can actually pick up people and hear people on the net that I just wouldn't otherwise be able to receive. Just a note on that antenna protector. This is quite a useful device to use, and the details are in the paper if you want to make one and how they work. But simply, it's a it's almost an unbalanced, it's not bidirectional. You can actually, the received signal will come through this way here and through a light bulb and out to your receiver or your antenna port on your transceiver. If you accidentally transmit RF this back into it, which can happen quite easily, and I've just touched my mouse and I shouldn't have, what will happen then is the RF will come back this way, it'll go through the light bulb and tend to light it up, so it'll increase its resistance, and then it gets to here and the diodes will prevent any more than about 0.6 of a volt forming here as it takes the RF to earth. So it thereby protects, it doesn't allow any RF to really of any significance to get back into the active antenna. And so this little box here, or little bit of protection is quite useful if you think you might accidentally give a backblast of RF into your active loop antenna. It's a lot easier to replace the light bulb than to have to repair the antenna amplifier. So what we've covered in this presentation is explained what active loops are, that you really do need a TR switch if you're going to be experimenting with this and allowing it to transmit. We've also briefly looked at transmitting loop design as a reference to the designs that are used here for reception, and then looked at the receive-only mag loop designs and the ones that I've actually tested. And in the experimental designs of active loops, there's that one that's detailed in the paper which will show you how you can build a loop that will cover all bands, and you can work out how to tune that using varactor diodes. We've also given the types of diodes that you use. They're available from China, and it's just a few dollars for a handful of them. Looked at the tests and assessments in actual use. I've been using them for about 3 months on our nets that we have sort of 2 or 3 times a week. And I now have a good understanding of how good they are. They are practical. We've commented on commercial broadband active loops. I don't have a lot of information on those, but you can certainly do your own research on those and hear other people's reviews of them. And I think these loops have got a lot of advantages over the broadband loops. So unlike a transmitting mag loop, the loop conductor losses or the size of the loop is not critical for good receiving performance. And relaxing several design parameters make it for a very adaptable receiving antenna, and also certainly very cheap. The experiments described here about thin wire and thick coax antennas show there's a lot of potential to adapt these and use these in a wide variety of amateur station situations. And by that, it means using them as portable antennas. Certainly the thin wire one is something you could rig up out of a backpack. And that's that. Questions?